Hey there and welcome to The Explainer. If you're the kind of focused learner who just loves breaking down complex, messy systems into clear, actionable pieces, well, you are in exactly the right place today. We're going to dive into a pretty fascinating engineering detective story involving an Airbus A320 air conditioning failure. But we aren't just looking at what broke. We're going to systematically investigate it by creating a simple FMEA, a failure mode and effects analysis table for the aircraft's AC system. It's basically the ultimate tool for turning a chaotic breakdown into a perfectly structured, solvable puzzle. So, to set the stage here, imagine you're an aircraft technician doing a quick turnaround inspection on a narrow-body A320. The clock is absolutely ticking. The flight crew comes out and reports that the aft cabin, the back of the plane, is completely sweltering. Passengers are boarding soon, and we all know sweaty passengers very quickly turn into angry passengers. And to make matters worse, your systems checks show that the Pack 2 temperature is running dangerously hot. It's right on the edge of a total system overheat.
Okay, so you step out onto the tarmac and start digging into the machinery. Treating this whole thing like a crime scene, you gather up your initial raw symptoms. First up, the cabin temperature is just completely unstable. Second, the physical airflow actually reaching that aft cabin is noticeably weak. And third, the air conditioning pack itself is running at an abnormally high temperature. You do a quick physical sweep and note 3 rough observations: a dirty cooling fan, a small leak in the ducting, and a history of an intermittent temperature sensor fault. So, those are our clues.
To solve this mystery, here is our roadmap. First, meeting our 3 suspects. Second, building the FMEA table. Third, calculating risk. And fourth, developing a preventative maintenance strategy.
Let's jump into Section 1, meeting our 3 suspects.
Now, looking at the flow control and pack components, you can really visually anchor exactly where our suspects live within the complex web of the A320's pneumatic system. Notice the flow of bleed air moving through the heat exchangers, the air cycle machine, and those various sensors talking to the air conditioning system controllers. I mean, it looks incredibly complex, right? But identifying the exact location of our compromised components is the absolute first step in accurate fault isolation.
Right, so to properly investigate, we have to translate our generic tarmac findings into official Airbus nomenclature, complete with their functional item numbers, or FINs. That generic dirty cooling fan we saw, that's officially the air cycle machine, designated as 11HM1. The small ducting leak maps directly to the air conditioning ducting system. And that intermittent temperature sensor fault, that is specifically the pack temperature sensor, officially tagged as 32HH. All right, we've got our 3 formal suspects.
Moving right along to Section 2, building the FMEA table.
Time to pull out our primary forensic tool. We need to determine the function, failure mode, effect, cause, and existing control for each of these components. So, suspect number 1, the air cycle machine, or ACM. Its main function is lowering hot bleed air temperatures via heat exchange. The failure mode we're seeing is that it's clogged or dirty. And the effect? Well, it causes high pack temperatures and drastically lowers cooling efficiency, which matches our symptom perfectly. The root cause is just everyday dust and environmental accumulation. Currently, the control for this is a standard visual inspection during turnarounds, plus scheduled cleaning from the aircraft maintenance manual.
Let's look at suspect number 2, the air conditioning duct. Its function is pretty straightforward. It distributes conditioned air from the pack to the cabin. The failure mode here is a minor leak. The direct effect of that failure is weak airflow to the aft cabin and an unstable Pack 2 temperature simply because the system is losing pressure. The cause? Usually aircraft vibration leading to seal wear. The existing controls are your standard leak tests and visual inspections.
And then there's suspect number 3, the pack temperature sensor. Its function is to monitor system temperatures and provide inputs directly to the system controllers. The failure mode is an intermittent fault. And guys, this is a big one. The effect is totally unstable cabin temperature control and potentially false overheat warnings, which can trigger a massive cascade of automated shutdowns. The cause could be contamination or internal wiring degradation. Controls involve operational tests and resistance checks. The crucial takeaway here is that while a dirty fan makes things kind of warm, a faulty sensor literally lies to the computer, which can cripple the entire system.
Which brings us to Section 3, calculating risk, the verdict.
So, with the qualitative analysis done, it's time to actually quantify the threat. Based on our analysis results, which component is the most critical? We figure this out by calculating the risk priority number, or RPN, which multiplies 3 factors: severity, occurrence, and detection.
Let's look at how experts scored our suspects using field data. Severity measures the impact of the failure. Occurrence measures how often it happens, and detection measures how difficult it is to catch. Notice that sensor at the bottom? It has a massive severity score of 9 because it can cause an entire pack shutdown. Even worse, it has a detection difficulty of 7. Intermittent electrical faults are notoriously brutal to catch during a quick visual turnaround, especially compared to a dirty fan, which scores a highly detectable 2.
When we actually multiply those three numbers together, the gap in risk is it's staggering. The air cycle machine scores a relatively low 56. The duct leak sits right next to it at 60. But look at the pack temperature sensor. It shoots all the way up to 189. This visually isolates our culprit, showing us exactly where our maintenance priorities have to lie.
An RPN of 189 makes the pack temperature sensor, R32HH, the most critical component by an absolute landslide. While the dirty fan and the leaky duct are for sure contributing to the poor airflow, it's the sensor's intermittent failure that is lying to the controller, causing the system to overcompensate, totally destabilize the cabin temperature, and threaten an outright Pack 2 overheat. We have officially found our mastermind.
So how do we handle this in the real world? Well, taking a look at the actual Airbus troubleshooting manual, the TSM, specifically for verifying this pack temperature sensor. Because intermittent faults are so hard to detect, technicians have to perform a highly specific resistance check. They measure the ohms across specific pins at different temperatures to see if the sensor's internal wiring has degraded. If the resistance values fall out of these extremely tight specified limits, the sensor is officially condemned and has to be replaced right then and there.
Finally, let's head into Section 4, Preventative Maintenance Strategy. So we've isolated the mastermind, and we understand exactly how to test it. But our job isn't quite done. We don't just fix it and walk away. What is the appropriate preventative maintenance strategy here? The most effective approach integrates perfectly with the existing aircraft maintenance manual. Specifically, we have to rigorously enforce AMM Task 216300-100-801. This task actually goes beyond just the sensor itself. It requires technicians to access components 21HK, 22HK, and 23HK to perform a scheduled cleaning of both the sensor ducting and the temperature sensor. Keeping these components free from the exact contamination that causes those intermittent electrical faults is our #1 defense.
But you know, a task is really only as good as its schedule. Adhering strictly to the Airbus engineering intervals is vital. After a fresh installation or cleaning at 0 hours, the absolute limit for the very next mandatory cleaning is 7,500 flight hours, or a calendar limit of 72 months, whichever comes first. By strictly enforcing this timeline based on our FMEA data, we significantly lower that occurrence score, dragging that massive 189 RPN way down to a safe, manageable level.
And just like that, boom, you've solved the Pack 2 overheat mystery. You took a chaotic, sweltering cabin situation, mapped out the system, applied the FMEA methodology to quantify the risks, and deployed a highly targeted preventative maintenance strategy. It's exactly this kind of structured approach that keeps aviation so incredibly safe and reliable. So I'll leave you with this final thought: the FMEA framework. It's completely universal. It works on literally everything from avionics to hydraulics. So what critical system will you analyze next? Keep analyzing, keep learning, and I will see you in the next explainer.